Okay, last lecture we stopped at this composite chapter. So we have two cases. One is iso strain and iso stress. What I mean by iso strain? When you have a composite that the layer go by this way, and your forces so when your force is perpendicular to this surface and the composite layer is by this orientation, right? Like what you see on the screen. You're going to use this equation. Elongation, modulus Young composite, which is the total composite, will equal to modulus Young multiplied by the volume of the component. So you know that your composite consists of two things only, which is fiber and matrix. Matrix is the resin. Okay, so you use this equation for this isostrain behavior. All right. Okay. And from this equation, remember to apply Hooke's law, which is E equal to stress strain. Meaning you can convert all this highlighted equation here into Hooke's law. Means you can find the stress and strain from here. Okay. Okay. So one thing is when it's isostrain means deformation. Iso means same deformation. So when you substitute this equation into here, your strain is the same. So you can cancel the parameter and you arrive at the equation that you needed. Okay. Okay, so the derivation we already covered in the previous lecture. All right. So this is called the one that I highlight here, rule of binary composite. Rules of a mixture of binary. Binary means two component. You have fiber and matrix. So this is isostrain condition. Don't confuse this condition with another condition. Okay. So this one you read. So by the same equation, you're using stress equal to force divided by area, and then you rearrange, you get stress equal to modulus Young multiplied by strain. This is Hooke's law, right? Hey, sorry, I write the wrong one. Hey, not this one. Hooke's law is stress equal to modulus Young. Okay, so this is Hooke's law, and this is isostrain, means composite strain or deformation will equal to the fiber and matrix strain. So when you do this ratio, when the question asks you to find the ratio of loads, the question asks you to find the ratio of loads on the fiber and matrix region, means what you do, if the question asks you to find the ratio of loads on fiber, means F fiber divided by F matrix. So by using the transformation of all these definitions, stress equal to force divided by area. So you change force equal to stress area, and then you further extend what is Hooke's law, stress equal to modulus Young and strain. Okay. Okay, then after that, because this is isostrain means the same deformation. This one you can cancel. Fiber strain divided by the metric strain. This one cancel, you arrive at this equation. Okay, so A, you know that A, how to find A because of the same thickness of the layer. You're finding the A multiplied by the thickness, you get volume. So A, you can convert to volume. So composite, sometimes you can find area, you can find volume. Okay, so this is very important formula lah. Okay, so these are the things that I write on the whiteboard here. Okay, now we apply this formula. So first, calculate the modulus of elasticity, which is the modulus Young, E, tensile strength, which is the stress, fraction of load, which is fraction of load carried by fiber followed by material, so F divided by matrix, right? So under isostrain condition, so you use this full set of equation 1, 2, and 3 to find the answer. So you are given the parameter so and so. So composite consists of continuous glass fiber, reinforced epoxy resin. So your fiber is glass fiber. Your matrix is epoxy resin. Okay, so it gives you percentage, 60% volume of the fiber having modulus elasticity of so and so, tensile strength so and so, and hardened epoxy with the modulus so and so. So given the tensile strength, the parameter here. So you need, in your answer, what we expect, you write the rule of binary composite, this one. Then you expand this one by using Hooke's law. Then you write this ratio between the force on the fiber and matrix. You extend. Okay. Then only you substitute. Then only you substitute value. So the first one, you write this one. I want this on the screen. Okay. How to derive this one? You need to refer back to the previous lecture, how we derive that one. Okay. All right. Now, it's always good to draw something on your answer. Like, for example, this is isostrain condition. Try to draw this diagram on your answer. Try to draw this diagram so that you can visualize what actually you are doing. Okay. Okay. Then you substitute fiber, modulus Young or elasticity. Volume is given, volume fraction. So volume fraction is 60% fiber. So you just put 0.6. Matrix is 0.4. Okay. Then you press calculator, you get the composite modulus elasticity. Okay. So again, this is when the question use the force, the E modulus in the longitudinal direction. Then you use this formula. So if the question mentioned, even the question didn't mention isostrain, it mentioned that the composite was stressed in the longitudinal direction. You use isostrain condition because you're pulling in the tensile, this one. So when you pull in this direction, because of this layer, you pull, the deformation actually the same. Matrix fiber is the same, right? The way it deform is the same. Okay, so this is E longitudinal direction. You know what is longitudinal and lateral, right? Okay, so this is longitudinal, this is lateral. Okay. Another one, tensile strength, same. You convert this formula. EC equal to modulus Young fiber multiplied by volume plus modulus Young matrix plus volume matrix. Of course, before the volume, you know that you can also use A also. But typically we use volume. So we change by using Hooke's law, stress equal to modulus Young and strain. Substitute these two, this one you rewrite inside there, right? So you will see this stress because it is isostrain, you cancel out the strain, right? When you substitute this one in, the strain you cancel out because it's the same. All right, then you substitute volume of composite 1, volume of fiber is 60%, 0.6, volume of matrix is 0.4. Okay, then you are given the tensile strength there. Okay, so you substitute the tensile strength accordingly, you get the composite strength. Okay, remember the unit. Remember the unit in Pascal. Pascal. All right. Now the fraction of load again is F versus M, versus M or fiber versus matrix. Same, you expand this one with F or stress definition. Stress equal to force divided by area. Apply Hooke's law. You convert this one in terms of E and V. E and V. So how to derive this one already explained in the lecture just now. So okay, so this one you can substitute value inside there by using this one, right? Or you can use this one is between fiber and matrix. This formula is composite. You use fiber versus composite. So this one is ask you to C1 is fraction of load carried by fiber for the following composite material. He asks you fiber versus composite and not fiber versus matrix. So don't like memorize and then go into the exam. Look carefully what the question asks you. Although you learn this one, but the question asks you fraction of load versus composite. So force of fiber versus composite. What's the definition of force? Already derived. Force of composite equal to this one. Okay, so you substitute this one, force equal to this one. Okay, then the rest is just substitution. Okay, so I only need to highlight the careless mistakes. Usually you do not read properly the question. You use this equation, then you get the wrong answer. Okay, read carefully. The question either asks you fraction of load carried by fiber and matrix. Means this one, you use this formula. If the question, like example 5, asks you to find fraction of load carried by fiber for the composite material, then you use F and C, not F and M. So this is the careless mistakes. Okay, so the answer will be 97%. Okay. The next one is called isostress, which is a new thing for today. So isostress, if you look at the diagram, it actually is another orientation. The layer orientation is different now. Just now, isostrain is vertical, but now isostress is horizontal. The layer is horizontal. Okay, so fiber matrix, fiber matrix, fiber matrix, and the load is at this area. Force or load, force or stress is the same, and pulling at both ends is a tensile loading. If it go inside, it's a compressive. So if the question mentioned compressive stress or compressive load, then the arrow will be pointing in. Read carefully. Your final will be very tricky. So Just be careful. Don't confuse, don't assume that I will always ask you tensile. Try to think what if the question asks you compressive stress. Okay. So this is a self-explanatory. So stress on the total composite will be the same. If you pull this direction, the stress acting on the whole composite will be the same as fiber matrix, fiber matrix, fiber matrix. The stress experienced by fiber matrix will be the same. Yeah. So the previously is isostrain. Now we'll look at isostress. The orientation of the laminate layer is different. So always read carefully what is the scenario you have for composite. Either is isostrain or isostress. Then they will ask you in section C, propose what is the better lamination method. Either is isostrain or isostress. Try to understand how we ask you question. Because we are more in your application. You're going to be, compress is the same actually. It's only the arrow is pointing in. Yes. It's only a negative sign only. Okay. Okay. But what is important is you know what is isostrain, what is isostress, and what is the lamination method. One is like horizontal orientation, one is vertical orientation. Okay. What's the difference? You cannot differentiate, man. You don't know how to differentiate. You know what is the orientation of the layer and the force acting is different. You don't know the difference. I draw this one. You don't know. You don't understand. Yeah, the line is means the green line. It means the layer. The layer is different. So, like for example, the isostrain is like that. It's like that. One layer like that. But the stress is like this direction. But isostress is like that. The stress still pointing up and down. Okay, the two layer orientation is different. Okay, because after this, you go into as an engineer, you need to tell your staff what is actually wrong with the design or why it's failed in a certain way. Maybe because of the composite orientation or how to optimize your design. You change the orientation of your composite. Okay, so we're back to isostress. Isostress means stress is the same. So when your stress is the same, your total strain of the composite will be total strain is a deformation of the composite will be the combination of fiber and matrix. Okay, the deformation that experienced by isostress condition will be the combination of fiber and matrix because matrix and fiber they elongate differently. When you pull it, it elongate differently. So the elongation here is a bit different between the material. So that's why you see the second formula on the screen here. Okay, then you expand using volume fraction. EC, why there's nothing there? Because your volume of composite is 1. VC, this elongation, strain, composite, there's a VC here. VC is 1. Then this one is the volume fraction. All right. So using Hooke's law, you rewrite this equation, right? So when it's isostress, you use another equation. When isostress, you are using EC plus EF VF plus strain matrix, volume matrix. Okay, but if you want to remember in the proper one is got VC here lah, but VC equal 1. Okay, this is 1. Okay, so don't confuse between isostrain equation and isostress. Huh? Isostrain, what is different is the modulus is different, but isostress, the strain is different because the fiber and matrix elongate differently in isostress. Okay, don't confuse, huh? Because when you come to test or final exam, there's so many things you need to remember. So don't confuse between these two. Right? So the rest is just, again, use Hooke's law again. You convert this equation into stress versus, you convert this one into stress and modulus Young. Right? So you convert this one into composite, stress and elongation, modulus Young. Here same, stress and modulus Young. Matrix also same, stress and modulus Young. Okay. So when you substitute into here, right, then you divide, you factor out all the stress. Because it's isostress, you factor out, you cancel the stress, you'll get 1 over E. Okay, you arrive at this equation. Okay, so the equation you get 1 over EC equal VF EF plus VM over EM, or you can expand it into same denominator. Same denominator means you find the common denominator lah. This side multiply by EM, this side multiply by EF. Okay, so mathematically, when you multiply the same denominator, you get this one, and then usually we don't like 1 over something. So what we do, we flip the thing. We flip the thing, we get this one. Huh? So either you remember this one and then you do the mathematics in the test, or you straight away remember the one I highlight in the box. It's quite lengthy. Depends on your preference lah. But this one will sure ask you one. Huh? Got 3 set. Each one have 3 set. One is this one. One is Hooke's law. Because this one help you to convert this one to the term that you need. Okay, you remember this one, remember Hooke's law. It depends on question. Whether question asks you stress or asks you for isostrain, of course it will be the same lah. Okay. So sometimes the question will ask you stupid question. It give you isostrain, it asks you the value of strain. Ask you to find value of strain. That is a bonus question actually. If the question give you isostrain, then ask you the value of strain. Sometimes you don't need to calculate. Sometimes you just need to read from the question. Answer is just read from the question, you write the question. If it's isostrain, but it's isostress, you cannot use. Isostress, you have to do the conversion. Like, okay, isostrain, you have 3 equations, this one, ratio. But remember, this one, the third one is quite tricky. It depending on the question. Like the example I show you. The question asks you to find fiber versus composite. Okay, but this one you remember, fiber and matrix. Then how you find the ratio is also same. By definition, what is stress? Stress equal to force divided by area. Then Hooke's law. You convert accordingly lah. Then isostress also got 3 set. 1, 2. Okay, 1, 2, or you can expand this one. Right? So this one again, if the question asks you E modulus elastic in transverse direction, then you use this one. This one is transverse direction. This one is in longitudinal direction. These are the keyword in the question. Sometimes the question didn't tell you whether it's isostrain or isostress, but it will tell you it's either longitudinal or transverse. Yeah. So that is the thing lah. Okay. So the rest is on the screen here. So this is longitudinal. This is transverse. Okay. Now, these are the graph or schematic presentation for tensile properties and volume fraction of fiber. So this is just to show you what happens if you increase the fiber percentage from 0%, 25%, 50%, 75%, and 100% of fiber. Of course, you know that when you increase fiber, you increase the tensile elastic modulus for the composite. Okay, so you will get isostrain is this one. Isostrain. Why you get a straight line? Why you get a straight line? This is a very common question. Why the blue line is in isostrain? I write on the whiteboard here already. Can you explain why the blue line is straight line? Why the blue line here for isostrain condition when you plot tensile modulus versus fraction of fiber? Why you get straight line? Oh, not straight line, linear equation. Linear graph. Why? Why the blue line is straight line? Yeah. Then what give you what equation? Can you see this equation? Loose or binary? This one is a linear equation. Can you see this one as a linear equation? What is the form of linear equation? Correct. Y equal to mx plus c. Now what you plot on the graph here? EC versus V what? Is what? Volume fraction of fiber. So it's V what? VF or VM? VF or VM? This one, this graph. VF, so this is VF. So EC versus VF, you get straight line. So what I write on the screen there, the first one, isostrain condition, what you have? EC equal to EF VF plus EM VM. Can you see Y equal to MX plus C? Okay, so your Y is EC, your X is VF, your M is actually your EF. Then what is your C? Your C is here. Okay, so if you're given a graph to analyze the question, you should able to use Cartesian approach to solve this equation. Can if you're given the chart like that and solve a composite condition, of course you'll see some value here. You should able to find the missing parameter. Okay, then if you understand why the blue line is a straight line, you should also understand why isostress like quadratic curve, or we call it polynomial graph or polynomial curve. If you look at this one, this is a polynomial graph. Okay, it's a polynomial graph. You can write them as a volume fraction of fiber if you want. Okay, so this graph or this graph will give you this shape, polynomial graph. Yeah, right. Okay, so the rest is very okay. Then this is additional notes. Okay, what is upper bound, lower bound, and so on. This is tungsten concentration versus composite E. This is composite tungsten dispersed in matrix, copper matrix, tungsten in copper matrix. And you have a upper bound, lower bound, means if you see these two curves, means this composite have two orientation. One is isostrain, one is isostress. Okay. So for composite, you need to do two experiments. One is isostress experiment, one is isostrain and isostress experiment. Then you get two graph here. Then after that, when you do the same experiment or in the factory floor, you want to see whether your products meeting the specification. You do the red line and blue line first. Then in the production, you QC department, you just ask operator, go and test the modulus young. Okay, if it's fall within these two, then still okay. It means in this region, means it's behave as expected. If it fall outside, means something wrong with the production process already. Okay. Okay. So these are another highlight lah. So when you see question longitudinal, you use the above one. If you use the question mentioned transverse direction, then you use the isostress equation. Okay. So look at example number 6. So this one is to calculate modulus of elasticity for composite material consists of 60% of volume fiber e-glass. E-glass fiber means your VF is 0.6. Resin is 0.4 for VFBM, you already have. When stressed under isostress condition, so this one is material is stressed perpendicular to the continuous fiber. So sometimes the question will be phrased as the material is stressed perpendicular to the continuous fiber, which is in this orientation. Okay. Sometimes you do not mention isostress condition. You mention the material is stressed perpendicular to the continuous fiber, means isostress. Okay. Then you given the modulus elasticity for both materials. You need to find modulus of elasticity. So same, either you remember or you derive from this one. It depends on which one is your preference. But it's the same at the end, you still get the same answer. Okay. It depends. Some people like this form, some people like this form. But both is the same thing. Okay, so this one, you just substitute the value. I only need to highlight is the 10 power 6 here. Sometimes the question do not give you 10 power 6. If you give you gigapascal, megapascal, kilopascal, you need to change accordingly. Okay, so these are the mistakes or some tricks that usually we like to test the student. Okay, we'll change the 10 power 6 into mega, kilo, and so on. So you substitute, you get the answer. Okay. So again, I highlight this one again because it's very, very important. If it's transverse, then use this equation. Okay, then the next is just a fabrication, how you fabricate it. Too bad we don't have a composite lab yet. Maybe before you graduate, you will see one. Okay, so how to make composite? So what you do, you need a mold, you need resin, you need fiber. So what you do, you have a contact mold with the shape that you want. Okay, then you pour in the laminate. Then before you pour in, you will put in a coating so that it's more easier to tear it out, right? So you spray a coating, then after that you pour it resin. You pour it resin. Then sometimes you need to use a tool to press it because it's a liquid form like a glue, so you need to do it. So laminate means one layer. You do it one layer by one layer and so on. Okay. So this is called hand layup process. You do it one layer by layer. So you put in matrix, you put in fiber, you pour, you roll it, you put in fiber again, the fiberglass, fiberglass, you cut it, and you need to wear PPE because fiberglass can cause lung infection and all this because it's very, very small, it's like a needle. So if you're not careful, you suck in the fiber, it will stay in your lung. It's like a small microplastic. So when you handle epoxy or not epoxy, you handle composite process, please wear the mask, the filter with the filter, not the normal patient COVID kind of mask. You have to wear the like people spray coating for your car. You need to wear that one, okay? Because of the fiber. Okay, hand lay process. So something like when you're making ship, so you see all these workers, they are wearing masks. Okay. Okay, another one is a spray. You use machine to spray. Same method also. Means you have a resin and spray. So this one I'll give you a spray like this one. Okay, so this is how people do when they do the boat body. So you have two methods here. One is spray, one is the hand layer. It's a combination two. The one that using the roller is the hand method. This one is the spray method. You just use it to spray. Again, this guy did not wear the mask. It's quite dangerous because the fiber is very, very small. The particle is when you suck inside, there is a hazard to your body. So they spray like that. This guy should wear mask. Yeah, it mix already. It mix together the resin and the resin and the fiber. They mix together already. So this one is like spray. This one is we can say is more uniform if you use spray method. More uniform. This one is a powder form. Fiberglass has a two form. It can be powder, means it's already like dry it already. And that one is like a plaster. It's a sheet of paper. So there are two forms. This one is like plain form. So I think for both one. And actually this one can make a lot of money. This composite. For the boat body. You try to go and ask how much is one boat for this one. You go and ask. Even a small one costs you like 50K or 100K. The process is actually very simple, but you need a very skillful staff. Yes. So another one is a vacuum. This one is like a small size, not like a boat, big one. So if you want to make like a spoiler for your sport car, right? So you make this, you use a vacuum bag autoclave process, right? So you put inside there like oven. You put everything in a seal mold, then you heat it up. This one most of the time will be in industry. This one in the industry. So this one is vacuum bag autoclave process. The part the important word here is vacuum. You vacuum it. The rest is still the same. You just use vacuum to press the material more evenly. Okay. Yeah, it's a cheaper, and also we call it a very low tech, low skill method. But this one you cannot you cannot be flexible in your shape. You have to, like, every time you have to make a new mold for that particular shape. Okay. So this one is the autoclave machine. It's like a big oven. You just put in there and let it cure. And this one is vacuum bag. So these are the material. So you see the fiber here is like a cloth there. So what they do, they put a sealant, and they start to put in. Need to make sure the mold is very very smooth. Not smooth lah, but clean surface, so that you will get a very smooth things. So this one is a pre-packed laminate. It's like laminate is like a plaster, you know, to stick the fiber together. So another material. There's layer by layer and so on. Okay, this one video you go and see or during your free time. It's quite a long video. And that one is called filament winding. This one is on the automation. Means I show you this one is a drum. You roll it, and then I show you the photo. Okay, so this one is the filament winding process. So you have all the filament in the string form, then go inside resin, join together, then pull into the roller. Okay, this one is a process used for the aircraft body and also for the rocket shuttle body. Okay. What happened to my... So you just you pull the composite string into the roller here. Roller here. Okay, you just mix the filament, the fiber in the string form, dip into the resin, then you pull into the coil. Then like a 3D printing or making cloth. So you will change orientation of the roller. So this one actually, it will change the orientation laminate layer of your composite. This is how they do the layer orientation. 45, 60, 30, and so on. Okay. So this one is compression molding, also can do composite also. Right. So this one is compression molding. This one is injection molding. So this one is injection molding video. This one, now we are in a fiber reinforced plastic composite material. Resin actually is a plastic. So what you do is just compress it, the injection molding, mix it, pour the material, solid material, plastic, part one, then go through a twisting element here. So you will slowly melt the temperature. This is a heat. You will transfer the material from heat zone position to nearby. Then there is a size on the material. Then you pass it into the that's the red stick. Okay. Another one is sheet molding. Sheet molding is in a sheet form. So there's a roller and so on. Let me show you, there's a picture. Okay. So this is how people make sheet molding. You will pull the fiber in the string form, then like making cloth lah. Like making cloth. So you pull the fiber. Then you chop it up. This one is they chop into a small strain so that they control the length of the fiber. No, this one is using they want to make a sheet, composite sheet. So they chop the fiber, mix with the resin. They come out like a cloth. They put two PE film on the both sides because if you do not wear gloves, you will feel itchy. You touch the thing because it's like a small needle. So you feel itchy after you handle. If you do not wear gloves, you handle composite material, then especially fiber. This is a fiberglass. Continuous protrusion, this is like you pull the thing out, like this is a
Pultrusion is a highly automated and continuous process dedicated to manufacture composite profiles.
This one is
35
you want
years
to make
ago,
a long
Epsilon
body
Composite was the first industrial company to combine the pultrusion process with high-performance materials such as carbon fibers and epoxy resin, targeting a wide range of applications and developing a unique know-how throughout the years. On a pultrusion line, spools of fibers are impregnated with a resin, then formed and solidified at the shape required into a heated die. A pulling system allows the process to run continuously, and profiles are automatically cut at the desired length. The process can run 24/7 with very few human interventions, which guarantees an outstanding productivity and consistency matched by no other composite manufacturing process. Reinforcements can be used in the form of spools of unidirectional rovings and tows, textile fabrics with oriented fibers.
This one you also watch lah. Okay, so we already come to a very advanced era where we start to mix metal inside there already. right? 20 years ago, 30 years ago, people mix fiberglass with resin, with plastic. But nowadays, we really start to use metal matrix composite. We call it MMC. So as you can see here, the different orientation. So this A1 is a continuous long fiber. B is a discontinued short fiber. And this one is a flex. Flex. Okay. So these are the table for material properties for different types of composite, continuous fiber, discontinued, particulate, and so on. This one is metal matrix. That's why you see aluminum inside there. Okay. And just now is metal matrix. This one is ceramic matrix. People start to mix ceramic inside there. So same, you have same three orientation of fiber: continuous, discontinued, or particulate. Same like this one is the ceramic matrix properties, Si and aluminum oxide matrix. Okay. Now another one, we look at the mechanism of ceramic matrix composite are believed to be toughened by three main mechanisms, okay, which all result from a reinforced fiber interfering with the crack propagation. How composite resists crack? So first, crack refraction. So crack refraction, there is a fiber there to block them from continue. This head, when you tear this one, the fiber actually, the fiber will continue to extend, and the crack can stop somewhere here. Okay, because the fiber still there. When you tear a fiberglass, tear a composite material, you'll see some string come out. Crack breathing and all this lah. Okay, so this one is a theory part. I will let you know if this one come out. So if it don't come out, then you need to mention. This one normally is a section A, question A kind of theory. You need to memorize and give the answer, right? So this slide is tell you that what are the three main mechanisms to make the ceramic matrix composite a bit tougher or stronger, right? Okay, now example 7 is an important one. We try to go through this one and then we call it a day, right? So now you have a metal matrix composite. Again, it's still a matrix problems or matrix question. Made of boron fiber reinforced aluminum alloy. To form boron fiber, tungsten wire is coated with boron, giving final radius 75 mm. So your boron fiber have a wire at the center and fiber at the B fiber at the outside. Okay. The radius is 10 micrometer. Micron is 10 power negative 6. Right. So this one is 20 is the diameter. So don't confuse by the diagram given in the question and the statement. Okay. Then give you the final diameter 150. In the question, it say radius 75, which is also correct. Right. Aluminum alloy is then bound around with boron fiber, given a volume fraction of 65% of aluminum alloy. So this fiber, it was bound with aluminum alloy matrix. Means you pour inside plastics or gel, right? Matrix. So you have fiber and matrix component. Okay, although there is a bombastic word here, but still composite only consists of two material, fiber and matrix. Okay, assume rule of binary matrix apply. Means these two, either is isostrain or that one. You need to determine. So calculate effective tensile elastic modulus of composite material under isostrain. So you're using these three set of equation. Okay. Or if you look at the diagram here, the orientation, right, is pulled in this direction. Okay, by looking at the diagram, you already know this is isostrain. The fiber orientation is vertical, right, with the stress or with the force. It's isostrain. You look at the one that I draw diagram here. The green color line and the force is same. Means the layer is parallel to the force. So it's under isostrain. Yeah. All right. Okay. So the question just now is here. Then I highlight the thing. So what you do? This is three materials. You have three materials. This only apply for two material, but this question have three material. You have a W wire fiber and the aluminum matrix. Your fiber have two. One is W, one is B. So continue, need to calculate this one. You just need to add one more. EC equal to fraction of W, E, right? And so on. Okay, and you know that W plus B equal to 35%. Because why? It gives you the matrix, aluminum matrix is 65%. So you know that W plus B is 35. It's a hidden message here. It's a hidden info. So fraction for aluminum is 65%. Okay. W. W, you need to calculate the ratio lah. Yeah. Diameter. Or you just calculate the area. Okay, the area. 2 pi r square. Okay, pi r square. Right? So you use area, is more precise because you can calculate volume also, but volume, the length is same. So volume you can convert into area. Okay, so you take area ratio. So FW equal to area of wire and the area of fiber multiply by 35%. Okay, this one you know lah, how to find the ratio of this blue dot here. So once you find it, you'll find the answer will be, fraction will be 6.2 10 power 3. This is ratio very, very small. Right. So you find what is FB. FB is a lot, right? Or when you find the W, you take this number minus, you take 35% minus this one. It's the same, Okay. For FB, because you already find the total is 35%. You already find the W percent. So you take this percent, this ratio, you take 30.35 minus this one, you get B. You understand? You understand this right, is a combination. So this is to find W. Once you have W, you can find B. Or you can use the same equation, calculate for B. It's the same. The same. Okay, done. You have all the fiber already substitute inside there. The E value is there. So from there you can find the composite modulus Young. This one is isostrain. Exam standard lah. You see, this is exam standard lah. But this one I show you this one because this is triple material. Yes. You can write VF. you can write V. This small, this F here, you can write V. Actually, it's a V lah. It's a volume fraction actually. Okay, it's a volume fraction. I use differently because this example 7 is a 3 material and not same like the previous one. Okay. So, but again, it's still two main ingredient, fiber and matrix. No, are you F because this question you have 3 different material. The previous one is only 2 ma. You can use V also actually. It means that if you want to use this one, how you write, your answer will be, you can write like one. EC, if example 7, EC equal to EF1 VF1 plus EF2 VF2 plus EM VM. So this one you can substitute as either B or W lah. Doesn't matter, you flip the sequence, doesn't matter. As long as you know what is fiber, what is matrix. Yeah. This is very near to industry lah, because industry won't use only one material. Okay. Okay. Example 8 is another illustration. You see whether makes sense or not. You just observe the solution steps. So you're given metal matrix composite with aluminum alloy 80% and with the viscous 20%. Density of alloy is so and so. Calculate average density of the composite material. Here it asks you about density. So when you want to calculate density, you need volume. You need mass of that one. Right? You need mass. In this question, you don't have mass. You only have density. Right? So you need to assume something. Like assume in 1 kilogram how many components you have. Right? So here, I assume that I have 1 meter cube of material. So I have volume for alloy is 80%, 0.8, and 0.2% for fiber. Okay, this is an assumption you need to make. Okay. Okay. So when you have mass in 1 meter cube, what you do, you're given density. So you want to find the mass, you take 80% meter cube, multiply by the density, you get one value. You do the same for viscous. Then now you have the mass already. Okay. Now when you have the mass, you have total mass. So when the total mass, you're able to find the average density. How to find average density? You take total mass divided by 1 volume will be 2.84. This is very straightforward. CM cube can, but make sure you have the correct unit because this yeah, correct. Correct. So this one, another one example, you try to observe whether you understand or not, right? So this one is given you composite, given you a fiber and matrix. 2 things, fiber given, matrix given. Calculate tensile elastic, which is a capital E, of composite under isostrain again, and calculate stress at which crack will grow. Equation of crack, you learned before this, KIC, in one of chapter, under defect chapter. So the glass matrix, KIC is given, fiber is given. Calculate the stress at which cracks start to grow. So if you look at diagram, it's quite similar to example 7, but this one is isostress, so you use this equation. All right. So isostress, isostrain. Question already tell you isostrain. So you use EC equal to, again, this is a small f, you can replace with V, capital V, it's the same. So V matrix and fiber. Okay. Then you're given a diameter, the diameter of the fiber. So 80, and the radius diameter is 50 micron. You can find ratio also. Okay. So calculate ratio, refer to example 7 just now. You see the same, right? So F fraction of your silica will be 0.3% or 30%. So once you know one fiber, you know the matrix already, right? Another one is 70%, 0.7, minimum 2 decimal place, maximum 3 decimal place for this module. So when you find that, you know another one is another side. So you substitute the value, E is given, right? Capital E is given, you substitute all this value, you get the composite E, right? Now, once you find composite E, okay, you know that is isostrain condition, so the strain is the same. So when strain is the same, you want to find the KIC, the K, the crack. And you want to find the stress at which it cracked. So this model is quite easy. When you see stress, straight away pull out Hooke's law to solve it. Hooke's law, stress equal to capital E strain. So the strain is the same. So you rewrite the strain, you move the capital E to the left-hand side, stress divided by E. You put inside this equation. Okay. Then you substitute lah. So fracture begin at a given component when stress equal to KIC divided by square root of pi A, assuming Y equal to 1. Where do you see this one? You see in the chapter where we discuss about defect. Chapter 7, chapter 8, right? So it's a combination of what you learned previous chapter. This is a final exam kind of standard. So you'll see stress equal to KIC divided by square root of pi A. Okay, calculate minimum stress, the crack deformation. KIC is a critical crack coefficient. Okay. Okay, so you see this one for ceramic matrix, largest pre-axis floor is 10 meter cube in diameter. Remember that when we say defect, you have two types of defect. One is at the edge. This is A. One is in internal. This is 2A. So you need to remember what is this. So pre-existing floor, 10 micrometer in diameter. What do you think? Which case, this one or this one? The crack, either at the edge, at the side of the body or at the middle. Middle. How come it's the side? Pre-existing floor give you diameter already. It's inside here. So your crack is 2A. It give you in diameter 10 micron. So what is your A value? 5 micron. You need to be careful lah. Okay. So you need to understand when you give something, flaw means defect. Defect have two types. One is at the side of the body, A, or in the middle. In this case, we use 5 only and not 10. Okay. You substitute the value inside there. Okay. So this one is from here. This one equal to this one. And you know that the equation for stress of this one is equal to this one. So you substitute this one with this one over E IC. Okay, so you change this one to here. Then you substitute accordingly. You rearrange. You'll get composite elasticity You pull this one to here. Okay, you pull this one to here. Okay, so this one is when start to grow lah. Okay, and then you look at this one, SI fiber, notch 5 micron, actually the same. The A size is the same, also 5. This one also 5. Yeah. So no matter you use this one or no matter you use this one or this one, it will give you the same answer. Only the KIC value is different. In this case, we use ceramic this one. So ceramic this one is 2.4. Okay. You calculate. You need to do homework. This one you need to do so that you understand what value to use. Okay. No, for the first one, we calculate because it's asked you calculate the stress at which crack start to grow. You have two material here. Either it fail at matrix or it fail at fiber first. You need to find out the value, then you give the conclusion. So at the first step here, we use glass ceramic matrix. Then we calculate ceramic matrix. It gives you the composite stress. If you use this glass ceramic. Then you see the second step, it used the silicon fiber. Okay, you'll find different value. For silicon fiber, it's 500 something, near to 600 megapascal. And for glass fiber, it's 1000 something. So what is the answer? You have two options here, 1000 something megapascal or 600 megapascal. What is the answer? Yeah. Okay. So fiber will fail first. So your answer you need to write lah. You need to calculate these two. Then at the end you make conclusion. Okay. So this one will fail first because crack will start at fiber. Okay. Then if you're given the area of that one, you should able to find the force that make this thing fail. If you already have this stress already, means you have this stress already. If you're given the area, you ask you what is the force that will make this composite fail. Yeah, so you can use this example for this single fiber here. You have the area. You can find the force. Yeah. Okay, this one is also final exam question. Okay, we spend another 5 minutes just to go through how to solve this question. This is a final question, or it can be your test 2 question also. Okay, so you're given a object made of a composite. You're given the diameter 50, 70. Length is given. Length is 1 for convenience, right? So he asks you to do bending, stiffness, and this one you need to recall what you learned in your statics. You already take your static, right? Static, you learn bending, all these things. So this is a bit complex. This question is a design question. So given stiffness, specify allowed diffraction in bending, subject to 3-point bending, right? And the load is given to produce elastic, not more than this one. Okay, so this one is more towards final exam question. We combine mechanical properties and composite chapter together. Okay. Okay. So this one is how bending, what you learn in your statics, how to find the stress, MC divided by I, how to find the rectangular, tubular things, right? Okay. Then it's continue, it's quite lengthy. So you need to do following, decide which 4-fiber material, like given here, which fiber material, when embedded in epoxy matrix, meets the criteria. Okay. So resin is this one. You have 4 types of carbon fiber. You need to choose like which combination give you the best or meeting the criteria. Okay, this question is more like your test 1, question 2 kind of question. Okay, it's the same. You mix it, you calculate, then you give the proposal. Okay, so B, under this possible, select one fiber material that will yield lowest cost. One is on the mechanical engineering perspective, and another one is on the economic perspective. Because when you go out work, you not only need to make the structure strong, and you need to give the lowest cost possible to your boss. Or you open up your own company, you want to reduce the cost, right? So when you do quotation, you need to understand the economic dimension. So there is a cost over here. Okay, so there are 2 steps. One, you find the elastic modulus for the composite, then meet the criteria above. Then after that, you pick one, and then you calculate the cost. What is the cost for that one? So you see the procedure. Again, this one is from the table just now. How to find the key fraction. Okay, and there is a moment of inertia given this one. This one is your static lah. So we assume we already know these 2 formula. So you rearrange this one, you substitute this one, you pull the I inside here. You want to find the modulus Young. So you pull the E to the left, pull your Y to the bottom. Okay, basically it tells you this equation. Then you rearrange. So sharp design, you have DIDO. All this substitute inside there. Okay, you'll find one value there. Because the question give you the delta Y, this one. The customer say maximum it can only bend this so much. So you calculate, put inside these 2 equations, rearrange, you get the E target of the projects. That is one we want to achieve, this one. Okay, then you go to the composite already lah. So you know that your target is this one, you go mixing the material. Okay, again, EC equal to matrix plus fiber. Okay, to make the calculation easier, you focus on fiber volume fraction. So this is, once you find the volume fraction, you can 1 minus the thing lah. Okay, so you use the data in table, you compute the 4 combination. Okay, you compute this one and this one and the resin, this one and the resin, this one and resin, this one and the resin, and you're given the VF and VM. Okay. Okay. So you try to think the logic behind. So this is the table that you see in your question. So you have modulus Young, your density. So you can find based on modulus Young here by certain percentage. You have the E here, E fiber and E epoxy. So when you substitute into the equation, this one, what is the why or how we use this one, right? So okay, remember this table. You have E for fiber, E for resin, or matrix. So when you arrive at the final steps, you understand this one, right? You understand this equation, right? You understand this equation, right? EC you have already. This is the customer requirement. Okay. Now from the table you have this one and this one. Okay. Once you have this one, then you have the mixing ratio. You'll find the, okay, this one, Okay, this one you customer given or you calculate already, 60 something, 69.3. This one's from table. V you can find, right? Not from table. There are these two numbers actually correlated. So this equation you have two unknown, right? But these two unknown is linked. You transform this one. How do you find matrix? You use 1 minus this volumetric fiber, right? So you convert this one in terms of one same parameter. So you only have one unknown. If you change Vm into 1 minus Vf, this equation you only have one unknown. Understand? So this one you find Vf first. This one and this equation you find Vf. Once you find Vf, you can find your Vm, right? So you get the first one. You find Vf, you find your Vm. First combination. Then second one, you find second combination. This is the answer that we expect after you calculate. This is the answer that we expect from the calculation. No, not putting the value, but from the calculation, you'll find first combination is Vf how much, Vm how much. This is to calculate cost. Later, this one later. Okay. So now, so only 3 types possible because their Vf value is less than 0.6. Because in the answer, if you read carefully just now, there's a specification mentioned. Something here lah. Here, maximum allowed fiber volume fraction is 0.6. So when you build this table or you find out the answer, Vm maximum 0.6 means from this table 4 combination you find your Vf maximum 0.6. So this one gone already. So you cancel this one. So you only have three options. So you answer for the first one, we have 3 possible combination: carbon, resin, carbon standard modulus and resin, carbon immediate modulus with resin, carbon with high modulus with resin. Okay, then you you already find Vf just by this formula. You understand? So just now you understand how to find 0.9, right? Do the same for the rest. It's actually the same. No, answer not given. This actually is your answer. This one actually is what we expected from your answer. Okay. So once you have this one, you know that glass is gone. So you find the volume for the combination. So volume, how to find volume? Volume is pi r square divided by length, right? This one. How do you find volume for this pipe? Pi r square times length, but this one is a tube, so you find the outside minus inside, you get the tube. Okay. So you find this volume. You know that total volume for the pipe is 1000 something in cm cube. Then you know volume, you can calculate volume. You have this fraction already. Okay. So this fraction you convert into cost. So fiber, how many cm cube? You have, for example, 95% multiply 0.954 multiply this one, you get this number. So there is a fiber mass price. This one multiply this one, you get this one. Then the same 0.46 multiply this one, you get this one. Matrix multiply by the cost. Okay, multiply by the cost. You have the cost, then multiply total. Okay. Yes. You're given density just now, right?
Yeah.
This one. Okay, so you calculate 3 set of prices for that length of tube. You have costs. One is $68, $86, and $153. Which one you choose? Of course lah. You choose the lowest cost lah, because it's most economic, meeting the customer requirement. This is how you do the material selection in the question. Okay. Okay, with this we conclude composite and ceramic. Next week we will do in polymer already. Okay, so the deadline for your assignment and lab I write on the whiteboard there. Remember to enroll yourself into the Canvas when you submit your lab report. If not, you're not able to. Okay, we have done with our class. Make sure you sign your attendance.